Hi everyone, welcome to Lesson 4. Today's lesson is Sum and Difference Identities in our trigonometry unit. The first question we have here is our opener question. It's asking you the identity of this equation has a restriction of, and you want to list off all the restrictions on this one. Reminder that all the restrictions are usually found in anything that has a denominator. So right now I have two fractions technically, and I want to find the restriction on each denominator. Let's start with this one here on the left. We have secant x minus 1, and our denominator, what it can't be is it cannot equal 0, because if you had a numerator divided by 0, you'll end up with an undefined solution or an error. From here, I'm just going to move that 1 to the other side, so I have secant x cannot equal positive 1 now. And of course, I can say something along the lines of secant is the same thing as 1 over cos x cannot equal 1. From here, you basically want to evaluate and find where and get cos x by itself, and then evaluate when that actually occurs. So here, I'm just going to do a quick switch. So this is cos x cannot equal 1. So again, I'm going to take a look at my grid. I have 1, 0, 0, 1, negative 1, 0, and 0, negative 1. The only position where cos x is equal to 1 is right here at 0 degrees. So right away we can say something along the lines of x cannot equal 0 degrees, and you want to have that every time. So plus 2, let's go 2 pi n, for n is an element of an integer, and so basically I wrote my restriction in terms of radian, and that's perfectly fine. The other restriction we have is going to be right here. So we have cos x minus 1 again cannot equal 0. So here you have cos x cannot equal 1, sorry. And then so here if you have cannot equal 1, you'll end up with the same restriction as right here. So you'll have x cannot equal between basically 2 pi n, where n is an element of an integer. So I could have cleaned up this equation as well so that these two look the same. So um, cannot equal 2 pi n, n is an element of an integer down here. So these are the most two commonly seen restrictions. There's one not so commonly seen, and I'm just going to do that over here in a different color. The third one, the third restriction that isn't seen as often is literally right here. It was part of our first equation. We had 1 divided by cos x cannot equal 1, and then we manipulated to get cos x cannot equal 1. But right here, this one position here, cos x, in this position here, what we wanted was that cos x, so that cos x there could not equal 0 in this one position, because if you were 0 here, you couldn't continue on with this restriction anyway. So here, cos x cannot equal 0. So when does that occur? So we have two positions where cos was 0. So I can say x cannot equal, and that looks to be at pi over 2 and 3 pi over 2. So I'm just going to go plus pi n, where n is an element of an integer. So really you have two distinct restrictions, one that says x cannot equal 2 pi n, and one that says x cannot equal pi over 2 plus pi n. So those are our restrictions. Going into today's lesson, we have sum and difference identities. This is just a method to add angles. If you notice here, you have sine and you're adding two angles, cos you're adding two angles, tangent you're adding two angles. Each one of these have their own specific equations that you can use for sum identities. Vice versa, for difference identities, that's just a subtraction of two angles. And again, they have their particular outcomes or particular equations as well. All six of these equations should be found on your formula sheet, so you don't have to memorize it, you do need to know where to find it. It's about halfway down on the right hand side in your trigonometry section there. Previously, you were asked to find the exact value of sine 30 or tan pi over 4, which came from our special triangles. The question is, how would you find the exact value of sine 75? Well, first off, sine 75 is not an exact value that we normally work with on our unit circle. Our unit circle we usually work with 0, 30, 45, 60, 90 degrees. 75 is not one of them. So what could we do? The key here is we're basically going to break up 75 into two angles that are composed up of our standard 30, 45, 60, or 90. So how would you solve for the exact value of sine 75? You're going to choose two angles. Choose two angles with reference angles. With reference angles of, you want reference angles of 30 degrees, 45 degrees, and 60 degrees, because all three of these we know what the values are, especially off of a unit circle. So sine 75, how can I build it? I can definitely use an addition statement. I can do something like sine 75 is the same thing as saying sine. Let's go with our smaller angle first. Let's go 30 plus 45. And there you go. If we did 30 plus 45, it's the same thing as sine 75. And I know I could find sine 30. I know I could find sine 45. Those are straight off of our unit circle, so that there would work. Was there another way to do this? Usually, not. There's nothing that you could really subtract to get to 75 there. So 30 and 45, add addition would work. And please note that I did write my smaller angle first, bigger angle second. In the first example here, we have find the exact value of the following, cos pi over 12. Well, if you're really strong with fractions, you can leave this pi over 12 and work with it all in terms of radian, or you can just quickly convert this over to degrees. This is the same thing as asking you what's cos of 15 degrees. Well, I can't really add to get to 15 degrees. I would have to subtract two angles out of my reference. So I would say something along the lines of cos. I can say it's going to be cos of 45 minus 30. That's going to be 15, of course. So 45 minus 30 is equal to 15. Great. From here, if I have my subtraction difference equation for cos, I'm going to just set up my equation. So this is going to say cos A. So A is 45. Cos B, and B is 30, by the way, not negative 30, it's just the straight 30. And this is going to be added to sine A. And again, A was 45. Sine B, which was 30. And again, no negative on there. From here, you're just going to evaluate and or solve each piece off of your unit circle, or however you've remembered these angles. So cos 45 is the same thing as root 2 over 2, and notice that I left it as root 2 over 2, not a decimal. Why? Because it's at exact values. Cos at 30 degrees, we're looking at root 3 over 2 plus sine 45. Sine 45, of course, is root 2 over 2 again. Sine 30 this time, sine 30 is going to be just 1/2. Great. Now that we've gotten rid of all the trig statements and we're just left with these fractions, we're just going to combine our fractions. On the left here, if you're multiplying, you would end up with root 6 over 4 plus root 2 over 4. From here, I'm going to clean it up one more time. I can't combine my radicals, so I'm going to write them side by side. So I have root 6 plus root 2, but I can combine my denominator. When adding, it just becomes 4. For tangent 105 degrees, I'm going to find two angles that add up to 105. So I'm thinking of tangent, let's go with 45 and 60. Because 45 plus 60 is 105. So for tangent, let's take a look at our equation. We're adding, so I want tan A up top, so tan 45 plus tan 60, and all of that's going to be divided by 1 minus tan 45 tan 60. All right. From here, we want to evaluate as many of these as possible. So here we go. Tan 45. And again, at 45 degrees, your root 2 over 2, root 2 over 2. So tan is always sine divided by cos. So here, tangent at 45 is just going to become 1. You're going to add on tan of 60. Well, tan at 60 is the same thing as saying root 3 over 2. And so I'm going to write this one out in full. Root 3 over 2 is being divided by 1 half. That's tan 60. Below that, we have the 1 minus tan 45. Again, tan 45, of course, is root 2 over 2 divided by root 2 over 2. This here is just 1. And tan 60 again. And again, it's going to be the same thing here. So let's quickly jot that down. So we have root 3 over 2. And all of that's divided by 1 half. Let's clean this up as best as we can. So in my numerator, I have 1 plus root 3 over 2. The 2's cancelled. There's root 3 over 1, so it's just root 3 left over there. Denominator we have here is 1 minus, and this is going to be just multiplied in. That's just root 3. And there we have it. This is more or less our answer. From here, though, there's one thing that we can't have, and it's this radical in the denominator. What we want to do is get rid of that radical in the denominator by using your conjugate. Using conjugate because we have a binomial in your denominator. So what is your conjugate? It's the opposite of your denominator. So if I have 1 minus root 3, it's going to be 1 plus root 3. 1 plus root 3. So I'm multiplying both numerator and denominator by this conjugate, and then I'm going to simplify and see what we end up with. So in my numerator, if I'm multiplying, I'm just going to basically FOIL this all out. So 1 and 1 make 1. I have root 3 and another root 3, so that's plus 2 root 3's. And then I have root 3 times root 3, which is just 3. So that's all of my numerator. My denominator, I have 1 and 1, which is 1. Plus root 3 minus root 3 will cancel out, and then negative root 3 times a root 3 is just minus 3 there in your denominator. Let's clean this up one more time and see what we get. Here, numerator, I have 4 plus 2 root 3. Denominator 1 minus 3, of course, is just negative 2. Here, because we can divide everything by 2, I'm going to end up with negative 2 minus root 3. And there we go. This here is our answer. That's our solution in the exact values. In the next example, we have secant 5 pi over 12. And again, I'm not too worried about working with fractions. I can switch that out from a radical into degrees. So radians into degrees. Sorry about that. So I'm going to rewrite this as secant 5 pi over 12 is the same thing as 75 degrees. So you want to find, and let's quickly rewrite secant because that doesn't work for us. Secant is the same thing as 1 over cos 75, and that's what we want to find is cos 75 there. Well, what's the same thing? We can say something like cos 75 is the same thing as saying cos 30 plus 45. So that's the same thing as saying, let's go down a line. And of course there's that 1 there still, 1 still here. This is the same thing as saying cos 30 cos 45 minus sine 30 sine 45. And of course this line is right on top of everything. Let's get the exact values of everything in our denominator. Numerator is still just that one there. Denominator now root 3 over 2 root 2 over 2 minus 1 half and root 2 over 2. And there we go. Here we're going to try our best to clean this up in our denominator. And this is now root 6 over 4 minus root 2 over 4. Okay. And then from here, you can do a quick combining. So this is the same thing as 1 divided by root 6 minus root 2, all of that over 4. And from here, I'm just going to continue on with my notes up here. So from here, I'm going to reciprocate. So I have 4 over root 6 minus root 2. And of course, we can't ever have a radical in our denominator, so I'm going to use a conjugate. So I multiply top and bottom by root 6 plus root 2. There we go. So then we end up with 4 root 6 plus 4 root 2. And all that's going to be divided by 6 minus 2. From here, let's clean that up. So I got 4 root 6 plus 4 root 2, all divided by 4. And again, you could just factor everything, all the 4's out, or divide them all out. So you're left with just root 6 plus root 2. Leaving it in exact values there, we should be good. That should be our solution right here. In the next example, it says simplify as an exact value. So I gave you sine 100 cos 10 minus sine 10 cos 100. What you want to do is take a look at your formula sheet and match this up to one of your trigonometry identities. So here, if I have sine cos and then a subtraction of another sine cos, the only one where sine and cos is being subtracted is if we're using sine minus sine a minus b. So I'm just going to quickly fill in my a and b. This is the same thing as sine 100 because that's the first number minus 10. That should be our second number. That's going to be a and b. So here this is the same thing as looking for sine 90. And of course, if you can evaluate sine 90, that's the same thing as saying 1. There we go. In the next example here, same thing. We're looking at something that says sine cos plus sine cos. The only time that we're adding is if we have this here, if we're going sine a plus b. So we have here, let's fill it in. A is going to be pi over 6. Then b is going to be pi over 3. And again, of course, this is the same thing saying 30 plus 60, which is just 90, which is sine pi over 2. And if we know it's 90 here, 90 degrees or pi over 2, let's just look for that again. So 90 sine there should just be 1, and this is the same thing, but in this case here we worked in all radian. In example 3, it says simplify the following. So again, we just want to match this up to our formula sheet here. So I see a tan minus tan. So I know that there's only one option for a tan minus tan. It's going to be to fill in tangent of a minus b. So here we go. We have tangent. A should be my first term here, so that's going to be the 2 pi over 5. B is going to be my next one, so it's minus 3 pi over 20. There we go. And from here, what you want to do is convert these into common denominators so that we can subtract. So here on the left, 2 over 5 becomes 8/20ths. And you're minusing off 3 pi over 20. So you're left with 10 of 5 pi over 20. And of course we should clean up that fraction there. 5 pi over 20 is the same thing as saying tangent pi over 4. And of course we know tangent pi over 4 is root 2 over 2, root 2 over 2. So then that's equal to just 1. Simplifies up to just exactly 1. In the next example, example 4, it says solve sine x plus pi over 4 plus sine x minus pi over 4, and all of that has to equal 1, where x has to be between this restriction of between 0 and 2 pi. So first things first, I'm just going to rewrite out my equation here. There we go. So I'm going to rewrite this as negative 1 equals, well, if I'm adding, I'm going to go sine x, because we don't know what x is, cos pi over 4. That's going to be added to a cos x sine pi over 4. Okay, and so that's our first bracket there that we just rewrote out. And then our second bracket we have plus. So if this case we're subtracting, this is going to be sine x cos pi over 4. And it's going to be subtracted from cos x sine pi over 4. From here, I'm going to take a look at my equation. I can drop my brackets because it's just an addition sign in between them. If I have anything in common, I'm just going to cancel out. I do have something in common. I see a plus cos x sine pi over 4 minus cos x sine pi over 4. This entire term and this entire term will just cancel out. So what are we left with? We have negative 1 equals 2 sine x and x cos pi over 4. There we go. From here, if you can evaluate, let's try to evaluate. I know what cos pi over 4 is, so I'm just going to attempt to evaluate. I don't know what sine x is, so I leave this alone for now. But cos pi over 4, that's the same thing as saying root 2 over 2. Okay, so we did a quick evaluating. From here, I can take this root 2 over 2, multiply by 2. My 2's will cancel each other out. So now I have negative 1 equals root 2 multiplied by sine x. Again, let's try to get sine x by itself now, so we have enough space. I'm going to go negative 1 divided by root 2, so I divided off that root 2 is equal to sine x. And then here, we never like our denominator with radicals, so I could say sine x is equal to negative root 2 over 2. And of course, we could look that up or figure out our reference, whatever works there. So I'm just going to do it using our grid CA ST. I'm looking for when for when sine is equal to negative. Your negative right here and right here in quadrants 3 and 4. And so if I found x, so x equals sine inverse of negative root 2 over 2, and of course that's just going to get us negative 45, so our reference angle there, so x equals negative 45, so our reference angle has to equal 45 degrees, so therefore we have 45 right here, 45 right here, so I'm looking at x equals ultimately 225 degrees and 315 degrees. And there we go. We did want to have our answer in terms of radian because that's what our domain was, so let's switch both of these over. I can say now x equals 5 pi over 4 and 7 pi over 4. And there we have it. This here is our solution. Okay. And last but not least, we have example 5 here. It says, given cos A and a cos B both have fractions on them, where A is between 0 and pi over 2, which is 0 and 90 degrees, by the way, so you're in quadrant 1, and B is between 3 pi over 2 and 2 pi, so you're in quadrant 4 for B. Find the exact value of cos A plus B. So first things first, I'm going to do a quick sketch. So I have quadrant 1, because that's where A is going to be. So I'm going to do a quick sketch. Let's do something that looks like this. Cos is using the adjacent, and A is right here, by the way. Cos uses adjacent and hypotenuse, so I know 3 goes here, 5 goes right here. I would have to find my opposite side there if I needed. On B, again, I'm going to draw out a picture here. I'm in quadrant 4, so it looks something like this. And again, we have our B value right here. Uses our adjacent side, which is 5, and our hypotenuse of 13 right there. Okay. And again, we definitely want to find this last missing side here. So running Pythagoras for both, I'm just going to call that missing side there. Let's call it y and y. We're going to have two different y values. Running Pythagoras on this triangle here on the left, y here is going to equal 4. Over here on the right, running Pythagoras, y here is equal to 12. So I'm going to write negative 12 here because we're going down for this one here, and everything else should be good. Find the exact value of cos A plus B. So let's find that. So I can write out cos A plus B is equal to, and let's write down our equation. This is the same thing as saying cos A, cos B, minus sine A, sine B. I know more or less A's and B's because they're just sides, so I can rewrite this as cos A. Well, cos of A, this is triangle A, cos uses adjacent and hypotenuse, so cos A is just 3 over 5. Cos at B, B is this second triangle here. Cos is going to be using our adjacent 5, our hypotenuse of 13. So it's going to be 5 over 13. We're going to subtract off sine A. Sine uses opposite and hypotenuse, so sine A is just 4 over 5. And sine B, which again uses opposite over hypotenuse, which is negative 12 over 13. From here, I'm just going to multiply my fractions together, and try your best to reduce as well. So here you'd have 15 over 65. We're subtracting off, what is that? Looks like negative 48 over 65 again. Okay. So really, here you are adding because you have minus a negative, so that's really just adding. So I'm going to go 15 plus 48 there because I have common denominator already. So 15 and 48 is 63 all over 65. So that's what cos A plus B is equal to. It's this exact value of 63 over 65. And that's the end of our lesson today for sum and difference. If you have any questions, please feel free to ask.